Okay, our final lesson of Chapter 8 is on binomial probability. And first of all, in order to calculate a binomial probability, you have to have a binomial experiment. Well, how do you know if you have a binomial experiment? That's the first thing you're going to kind of work on. But basically, every question that's thrown at you on the test will probably be a binomial experiment. I'm not sure I'll really ask you to identify between the two, but we'll go ahead and practice that skill anyway. So in order for something to be a binomial experiment, you need to have repeated situations, which we call a trial. So for example, throwing a die, right? You pick up the die, you throw it, that's the first trial. You pick it up again, you throw it a second time, second trial. So we could repeat that as many times as we wanted. The second thing you need to make sure you have is that there's two possible outcomes, success and failure. Well, for the die, we can still have a probability, a binomial probability, because I could say, you know, what is the probability of rolling a 3? So the success would be rolling a 3, which would be 1/6, and the failure would be not rolling a 3, which would be 5/6 of a chance. So that also works for only two possible outcomes. The trials must be independent. Well, if I pick up the die and I roll it, and then I pick it up again and roll it a different time, whatever I rolled the first time has no impact on what I roll the second time, so they're independent of one another. Each trial has the same probability of success, so my chances of rolling a 3 for the die are the same every single time I pick it up. It's a 1/6 chance. And the experiment has a fixed number of trials. Well, I can just say out of 10 times, what's the probability of rolling a 3? Something like that. Okay, so let's try to identify whether or not these experiments are binomial from this list. Let's keep the list there. So tossing a coin 20 times to see how many tails occur. So tossing a coin 20 times. Does it have a repeated situation? Yes. Are there only two possible outcomes? Yes, that would be heads or tails. The success would be tails, the heads would be failure. Is one independent of the other? Yes. And do we have a fixed number of trials? Yes, we do. So I would say yes, this is an example of a binomial experiment. Rolling a die until a 5 appears. Okay, no, that's not a binomial experiment. Why? Well, until a 5 appears, that doesn't have a fixed number of trials. So this is false because it doesn't have a fixed number of trials. So I would say no to that one. The third one, rolling a die to see if a 5 appears. So rolling a die to see if a 5 appears. So that implies to me that we're just going to roll it once. It's either going to happen or not happen, so I would say yes. That is an example of a binomial experiment. Measuring 20 days to see if it rains or not. Yes, it's repeated. It's a fixed number. We have a success and failure, rain, no rain. One doesn't depend on the other, so I would say yes. That's true. Asking 20 people how old they are. No. Why not? Well, there's no two possible outcomes. How old are you? You know, you could be 1 or 0 to however age. So you could change that potentially into a binomial probability by saying, asking people whether or not they are 19, or asking 20 people whether or not they are 19. Then there's going to be success, which is you are 19, and failure, which is you are everything but 19. But right now, the way it's stated, that's not a binomial experiment. Next one. Drawing 5 cards from a deck for a poker hand. Well, no, again, there's not only two possible outcomes there, right? We could have many different possible outcomes for that 5-card hand, therefore, that's also a no. And the last one, shooting 20 free throws and either making or missing a shot. So yes, I have a definite amount. There's only two possible outcomes. One doesn't depend on the other. So I would go with yes there. All right. Now, how is this binomial probability? It's going to tie in with what we just learned last class, which was about the Pascal's triangle and binomial expansion. So we are going to use those same skills and apply them here. It says a coin is tossed 10 times. What is the probability that exactly 6 heads will occur? So however many times we have is the scenario, or the exponent, sorry, in the binomial expansion. So if I was going to toss a coin, I can either get heads as a result, which I'm calling H, or I can get tails as a result, which I'm calling T. So my two possible outcomes have to be the two variables inside your binomial, inside the parentheses, which is like your binomial expansion. Your exponent is the number of times you're going to do that event. So the number of trials, that is. So your exponent is your number of trials. And then we want exactly 6 heads. Well, if we were to expand this, right, we would have h to the 10th power plus 10h to the 9th power. Sorry, I'm trying to erase that. 10h to the 9th power, t to the 1st power, plus, and then we would keep going on and on. It would be h to the 8th power, t to the 2nd power with a new coefficient, plus a new coefficient, h to the 7, t to the 3, plus a new coefficient, h to the 6, t to the 4th. So remember, these exponents always need to add up to 10. 8 plus 2 is 10, 7 plus 3 is 10, 6 plus 4 is 10. Well, I'm stopping here. Why am I stopping here? Because it says, what is the probability that exactly 6 heads will occur? Well, right here, this means 6 heads have occurred and 4 tails have occurred. So in order to calculate this probability, I need to take heads to the 6th power times tails to the 4th power and multiply it by whatever coefficient should be here. Well, if you remember in our last one, our coefficient we got by doing the combination formula. And we took the total number of the exponent here, which is the number of trials in this case. So if this is a 10, then this is a 10 here, first number. And then what was our second number? Do you remember? That was represented by the letter K, which happens to be this number here. So it's 10, choose 4. You could even make a 10, choose 6. It's not going to matter. So we would calculate that, and then we'd have to calculate this answer and this answer. Okay, so what am I missing here? Well, I didn't give you a value for tossing heads or a value for tossing tails. So you need to do that. What is the probability of tossing a head? Well, that's 1 out of 2 chance. What is the probability of tossing a tail? That's 1 out of 2 chance. So therefore, I need to replace my probability of tossing heads right here, which is 1/2. Okay, so this is translating to 1/2 to the 6th power. My probability of tossing a tails, which is 1/2 to the 4th power. And then I need to calculate this with my calculator. Right, so 10, choose 4. Let me do that on my calculator. And I get 210. Right, so all these pieces are going like that. Now we just multiply it. So literally it's 210 times 1/2 to the 6th power times 1/2 to the 4th power. And I get approximately 0.2051. So what is the probability of exactly 6 heads? So it's about 20% chance. Every time I toss it 10 times. That's what that means. Right? 0.2051. So about 20% chance. So what do we need to do? We need to have our binomial expansion. Our exponent is the number of trials from the problem. You have your success and your failure. Heads, I just called it heads and tails. You might have wanted to call it S and F, right? Success was your heads, failure was your tails. The probability of success, find out each probability individually, and then I calculate the term I'm trying to find, plug in the appropriate numbers, and solve. Okay, so let's look at question number 2. It's very similar to question number 1, except instead of the word exactly, we have the word at least. So how is that going to impact the actual way we calculate this answer? By the way, here's a a list of what you should do. So if you want to follow a list, if you're not sure, then here it is from what I just did in this top problem. Sorry, I don't know what happens when I scroll, all this stuff disappears. Anyway, a coin is flipped 5 times. So this time our number of trials, instead of it being 10, it's going to be 5. So we have our success plus our failure to the 5th power. Again, a coin is flipped. So it says, how many of the possible outcomes have at least 2 heads? So I would say our probability of success is flipping a heads, right? And that's 1/2. Probability of failure is flipping a tails, which is 1/2. In this scenario, they just happen to be the same probability because there's only 2 possible outcomes, heads or tails. So it's 1/2 and 1/2. Okay, so the first thing we have to do is expand this binomial expression. So we have s to the 5th power plus 5s to the 4th power f to the 1st power plus, okay, now I'm stuck. Well, this is only to the 5th power, so I can use Pascal's triangle. So that's 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Remember, I'm adding these numbers above. So this is 1, and then 5, 10, 10, 5, 1. So here are my coefficients to the 5th power. So this is a 1, this is a 5, then I have a 5, then oh sorry, not a 5 there, excuse me. Then I have a 10, then I have a 10, then I have a 5, and then I have a 1 again. So this is s cubed f squared plus s squared f cubed plus s f to the 4th plus failure to the 5th. Well, at least 2 heads means my heads, which is my success, need to be 2 or more. So what I have to end up doing is adding all this information up right here. So I have to substitute in 1/2 here. This is to the 5th power. Sorry, I don't know what happened to this. I must have put an F there instead of a 5. It's s to the 5th power. So it's 1/2 to the 5th power plus 5 times 1/2 to the 4th power times 1/2 to the 1st power plus 10 times 1/2 to the 3rd power, 1/2 squared, plus 10, 1/2 squared times 1/2 to the 3rd power. Sorry. So add all that up, and that will be your approximate probability for rolling at least 2 heads. So the word at least means 2 or more heads. So again, that is why I'm doing 2 heads, 3 tails, 3 heads, 2 tails, 4 heads. So 2 or more heads is everything over here. So go ahead, I'm going to pause and calculate that, and you can compare. So when I plug it all into my calculator, I got 0.8125. So there's about an 81.25% chance that I would roll at least 2 heads as listed answering the question. So 0.8125, or you could say about an 81% chance. Now let's move on. Okay, sorry, moving on, I paused there. This time, I'll help you set it up, and then you can try to calculate it on your own and check with the second video because we're going to run out of time. But what I want you to notice is that our scenario is different. What is the probability of rolling a 6 with exactly 2 times and 6 rolls of the die? So this is the number of trials, so that is my power on my binomial. So I have success plus failure to the 6th power. But I'm rolling a 6, so my probability of success is rolling a 6, which is 1/6 of the chance. But my probability of failure, well, if I don't roll a 6, there's 5 other numbers that I have, so the failure is 5/6 chance. So when you plug those in at the end, those are the numbers you're going to plug in. So what you need to do now is expand this, or maybe you don't, exactly 2 times rolling a 6. So that means we need s to the 2nd power and f to what power? Well, remember those 2 exponents have to add up to this number right here. So this is going to be to the 4th power. So your final step is to get the coefficient right here. And remember, the coefficient is just using the combination, your total number here, which is 6, choose, and whatever you have here of 4. So go ahead and calculate this and then check your answer momentarily. So you should have gotten a 15 for the first one, then 1/6 squared, 4 to 5/6 to the fourth, and gotten 0.2009.